So this is Unit 1, Lesson 5 for AP Calculus. The unit is called Limits and Continuity. The lesson is called Algebraic Properties and Limits. What we're going to learn in this lesson is how do we determine limits of functions, sums, differences, products, and quotients. So first, a couple basic rules with limits. So if we let b and c be real numbers and n be some positive integer, we can have these three rules right here. So the limit as x approaches some number c of a constant b, the limit is equal to b. So for example, if the limit as x approaches 3 of 9, 9 is the function. If we graph the function 9, or x equals 9, it's just a flat line. So anywhere on this flat line, as x approaches anything, in this case 3, the limit is going to be 9, because all the y values are 9. Second one, the limit as x approaches c of x is going to be equal to c. So x is the graph of the line y equals x. So it's just that positive slope 1 line. And so whatever your limit is, you can just direct substitute your limit in for x. So if 3 is the input, the limit's going to approach 3 as the output. Third rule, limit as x approaches c of some x to the power of some integer n is just going to be c to the power of n. For example, the limit as x approaches 3 of x squared is just going to be 3 squared. So 3 is our input, 3 squared is our output. So now the nitty-gritty properties of limits. So if b and c are real numbers and n is a positive integer, and we say that the limit as x approaches c of f of x is some value L, and the limit as x approaches c of g of x is some value k, then these 5 rules apply. So the limit as x approaches c of some number b times f of x is going to be equal to just that b number times the limit. Sum or difference both works the same way. If we have the limit of two functions added or subtracted together, it's just equal to the limits added or subtracted together. Same thing with multiplication and division. Division has the caveat that g of x, or the denominator, cannot equal 0. And then we have the power 1, so if we have the limit as x approaches c of some function to a power n of some integer, it's equal to the limit to that power n. Let's look at some examples. So just to kind of have our basic limit rules and our properties on hand, we're going to evaluate the limits as examples A, B, and C examples all use the limit as x approaches 3 of some function f of x is going to be a limit of 5, and the limit as x approaches 3 of some function g of x is going to be 4. So we're going to use these numbers for these examples. So the limit as x approaches 3 of 7 f of x, or 7 times f of x, well, the limit as x approaches 3 of f of x is 5. So if we evaluate this, it's going to be 7 times 5. And that's super straight up, like simple example right there. This is calculus, so for a quiz, if you just put 7 times 5 for your answer, I'm going to mark that correct. In the previous coursework, we want you to simplify your answer as much as possible, but we're no longer focused on the algebra. We're focused on, do you understand the calculus going on here? And so if you put 7 times 5, that shows me you understand the calculus. I don't really care if you can simplify this any further. That's going to be the same for examples B and C. So if we look at B, we have the limit as x approaches 3 of g of x over f of x minus x squared plus 5. So the limit as x approaches 3 of g of x is going to be 4. Limit as x approaches 3 of f of x is going to be 5, so g of x over f of x becomes 4 over 5. X squared, we're just going to substitute 3 straight in for x, because this is not a function, it's just x. So we're going to say minus 3 squared plus 5. And again, I could simplify that, but this is calculus, so we're not going to really care too much about that. Example C, limit as x approaches 3 of f of x divided by 11 times the square root of g of x. So this rule right here, f of x divided by 11, is really the same as our multiplying principle. Because if you recall, dividing by 11 is going to be really the same thing conceptually as multiplying by 1 over 11. So this rule still applies to this problem, even though it looks like a fraction in division. So we're going to write 1 over 11 times our limit as x approaches 3 of f of x becomes 1 over 11 times 5, or you could put 5 over 11. And then the limit as x approaches 3 of g of x is 4, so it's times the square root of 4. We could simplify this again, but we're not going to. A couple more examples we added in. Limit as x approaches 5 of 7 is just going to be 7. That's our basic limit principle right here. And the limit as x approaches 5 of x is just going to be 5, another basic principle. So here's a quick note, and it's just a conceptual check. So the limit as x approaches, if we give this function f of x and g of x, graphically we can see that the limit as x approaches some value c, or in this case 0, the limits for f and g do not exist. Neither of them exist. If we add those functions together, or we compose them in this particular way, we can see that on the left side, the positive and the negative kind of cancel out, equals 0. Similarly, on the right side for each function, if we add those together, they cancel out, equals 0. And so even though the functions themselves, the limits do not exist at that particular point, we add those functions together, the limit at that same point does exist. So this can happen. Just because the limits of the functions don't exist doesn't mean that the limits of some function that contains those two functions doesn't exist. It's not the case. To drill that point down a little further, let's look at an example, and this is probably similar more to what you would see on like a quiz, hint hint wink wink. So the limit as x approaches 1 of g of h of x means we're going to find the limit as x approaches 1 of h of x first, and then whatever that output is, whatever that answer is, limit as x approaches 1 of h of x, that's going to be the input for the limit as x approaches that number of g. So what that looks like is we'll find the limit as x approaches 1 of h of x. So we'll look on our graph for h. At x equals 1, from the left and from the right, our limit approaches 2. So we can say the limit as x approaches 1 of g of h of x is equal to the limit as x approaches 2 of g of x. So now that's going to be our equivalent limit function here. So if we find the limit as x approaches 2 of g of x, we find our graph for g, we find our x value of 2, and we notice that from the left and from the right, we get different limits. So we can say because this is not, the left is, let's see, is -2, from the right it's 0. So because they're not the same, the limit does not exist. Now let's consider the limit as x approaches 1 of h of g of x. We'll first find the limit as x approaches 1 of g of x. So we'll take 1 and the function g. From the left and from the right, our function approaches a limit of 0. So we can say the limit as x approaches 1 of h of g of x is equal to the limit as x approaches 0 of h of x. So when we check our graph for h of x, we find 0. From the left and from the right, they both approach the limit of 0. So we say the limit as x approaches 0 of h of x is 0, or the limit for the original question is 0 as well. Some takeaways from this lesson. Hope that we're moving away from tables and working, after this, we're working more towards the equations themselves, and we kind of got into that a little bit this time. So we're hoping that we're continuing to build our confidence in evaluating limits of a function, and just kind of a stronger sense of how to go about looking at limits and how to understand the function, the limit as a function.